Yeah, thank you, Willa, for the kind introduction. Yes, indeed, I'm a user of TXRF and not on the metrology side, but still a user for the purpose of analysis of um, air pollutants, especially aerosols. And as such, I would like to present you two application examples in the next half an hour or so. And let's see how these samples will explain how useful TXRF in combination with cascade impactor sampling will be. For further information, I put here two websites, web addresses here for the information about the AeroMed project, in which part of the presentation is included, and also for the other example, which I will present at the end of my talk in the second half, there's a link to the publication, which is unfortunately only in German for those who are able to read it. Okay, so few words about BAM. BAM is a senior scientific technical federal institute which has responsibility to the German Federal Ministry of Economic Affairs and Climate Action. So we are a state institute, and our motto is safety in technology and chemistry, and we do it in a lot of fields which are listed here. Tasks such as statutory duties for technical safety, research and development. That is something which I'm working in, testing, also analysis approval. And one activity is consulting, not only to the government, but also to the industry. And of course, also contribution to standards and statutory regulations. Well, after this overlook, I just go directly into the topic. So why XRF-based aerosol analysis? First of all, aerosol, why is that a topic? So air pollution, and especially aerosols, are still the leading cause of environmentally related severe health effects. And that is something which has enough motivation in it to deal with the task of chemical analysis of aerosols. And you immediately see from the diagram here on the right-hand side why aerosols are so important for health. Here, if you look at this diagram, you see how particles of different sizes are deposited in the lung and in the respiratory tract in the human body. And well, the smaller particles, or to a given proportion, also the bigger particles up to 10 micrometer, will end up in different parts of the lung and will have inflammatory reaction, will stir up inflammatory reactions, or even the smallest particles, the smallest nano-sized particles may end in the bloodstream and have a direct toxic effect if they transport it to other organs, for instance. So we investigated cascade impact or aerosol sampling in combination with in situ TXRF elemental analysis, which I would like to abbreviate as SIS-TXRF. And I would like to show you on two examples why this is a versatile tool for aerosol analysis. This method can answer about quantity, exposure levels, and also the size distribution of elemental composition. And that is important to know if you want to do a risk assessment in combination with the exposure to aerosols, or risk mitigation, so ways to protect against exposure or to reduce air pollution sources, and of course the countermeasures such as, for instance, personal protection. That is important for the outdoor, where we have EU clean air directives, which identify key pollutants such as arsenic or cadmium or mercury or nickel or others. And these have to be measured, and the concentration of these key pollutants have to be measured and controlled, whether the limits are whether the real exposure is below the limit, and that is done mainly in air quality monitoring networks. So that is a framework of possible application of this technique for outdoors, but also indoors. This combination has quite nice fields of application. Indoor aerosols are described by a broad variety of sources, and combined with this, a broad variety also of chemical compositions of these aerosols. And the motivation here is, of course, in the industry, the safety and the consumer protection in the private field or in the consumer field. And many substances in the EU REACH framework have been regulated due to the fact that they may include particles which may become airborne and may pose a risk by inhalation of chemical substances into the body. So this is TXRF may then provide a very useful tool for measurement of emission, the quantification of emission and exposure, and also may play a role in health studies related with the evaluation of risks. So here for the outdoor application, you may see here a view on the air quality monitoring network in Europe. For instance, you see the green dots. Each dot stands for a measuring station where local measurements take place. And if the dot is green, that is data from 2016, the threshold values or the limits are met, or values are below the limits. And for different pollutants, here you see the data from 2016, and you may see that for arsenic, for instance, at several areas in Europe, the thresholds have not been met and the values are higher than allowed. And but you also can see that given the large area of Europe here, that the network of air quality monitoring stations is not so dense as you may probably expect. And it is not dense enough if you consider that the concentration of air pollutants is constantly going down over the last decade in Europe. And it might be a challenge to the standard methods to measure even lower air pollutants, the lower concentration of air pollutants in the ambient air. And that is another reason why mobile TXRF in combination with cascade impactor sampling may play a big role in enhancing these air quality monitoring networks, in providing tools for a better ability of following the concentrations on a time scale, following the behavior of different sources as indicated here, intermitting sources which may vary in rates, or sources which have a constant but small contribution to air pollution situation. And well, this can be achieved by the technique of TXRF. And I would like to show you now an application example that we did a couple of years ago. We tried out how good TXRF works in a field campaign. So we did not ask so much about the theoretical background of TXRF, but just applied it and wanted to know, does it work in a field environment? And so it is technically feasible to operate cascade impactor sampling and TXRF on the spot in the field. And secondly, how good is it in comparison to the ICP-MS, which is the traditional method? So with ICP-MS, you collect aerosol samples on filters and then digest the filters and do the ICP-MS analysis in order to quantify the air pollutants. I would like to show then another example which comes from indoors. And this example is the application, the analysis of laser printer particle emissions. And besides the quantity or the particle number concentrations, it's also very important to know the composition of these particles. Laser printer emissions are chemically complex, organic and inorganic species. We will later come back to that. But overall, if you go to indoors, there are many, many different sources and which have a quite distinct chemical signature. And just some are named here in the diagram. And well, each of it has potential health effects if you are exposed to a high level. Well, and that is something where TXRF can play a role in combination with other methods, which more or less are able to identify the organic component of aerosols, where TXRF is able to identify the elements, or even the elements in a particle size distribution. Okay, let's see how that works. The field campaign, yeah, as I said, the goal is just a demonstration of the field usability, and we did some empirical calibration strategies and tested them against the standard method, which is, as I said, filter sampling and ICP-MS, and we are able, or have been able, to identify elements in particle size fractions. That was, of course, the goal. And we have been able, during the field campaign, also to compare cascade impactors of different designs. Okay, let's go into the details here. Well, the standard PM element analysis in ambient measurements in the EU is PM10 sampling on site. And PM10 is the size fraction of aerosols below a size or a diameter of 10 micrometers, so from nano up to 10 micrometer in diameter. All these particles are collected onto a filter in such a device, and then you may take out the filter, as shown here. Here's a filter loaded, the dirty one, that is a loaded filter, and do a destructive sample conditioning and ICP-MS in order to identify the quantity of elemental air pollutants here. That is destructive method. It is it requires long sampling, and it has, for that reason, a poor time resolution and almost no size resolution, because it just integral samples as an integral over the whole size range in the PM10. And we may have to face sample transport biases, such as that the sample will change or will age when it is transported, will probably be contaminated during transport. And of course, one advantage of this method is that this is fully traceable to a reference, and that it is felt that the sensitivity under the given circumstances in the moment is fully sufficient. We end up with this method in the information about total mass concentrations of elements in the PM10 fractions. Well, on the other hand, PM analysis by TXRF works a little bit different. We use sampling and cascade impactors for sampling. For those who are not familiar with cascade impactors, these are devices which deposit particles on substrates or carriers by the inertia of particles. So if particles are accelerated through a jet, as shown here, the bigger ones may not make it to the next stage just by their inertia and are deposited on a substrate, while the smaller ones will make it to the next stage where the situation is slightly different, so that these then will be captured on this stage, and then again the smaller ones will reach the next stage, and so on. And each of these stages has a so-called cut point, where 50% of the particles of that given cut point will be deposited on that stage, meaning that, for instance, in stage 1 here, 5 micrometer particles will be deposited here with 50% probability. And here you see these two cascade impactors, which we have used in the field campaign. I will then explain them a little bit in more details later. And well, what is the advantage? We have very short, or we may have very short sampling times, less than 6 hours, or depending on the level of air pollution. But we definitely have better time resolution. We have size resolution because, well, if the cascade impactor provides several stages, we have the possibility of analyzing each of the stages separately. So we have the size resolution of the elemental analysis. Cascade impactors as well as TXRF spectrometers are now mobile and rugged enough to work them in an environment, to transport them to a spot of investigation. But one drawback, or one, I would not say disadvantage, but one challenge is that it is at the moment required to manually assemble and disassemble the samples. So you need to mount fresh substrates on such a sample carrier holder, and you have to dismount the samples after loading and manually plug them or mount them into the instrument and to the TXRF. One advantage is definitely that this method is non-destructive, so you may then, after first analysis in the field, do a second analysis with other setup, with other instrumentation later in the lab if you're interested in some more details of the samples. And so that is quite a nice feature of this method. The method has also sufficient sensitivity, and last but not least, the question of traceability is here. I leave here a question mark for the moment, because traceability is something which has to be dealt with, and it is not so easy to fulfill the full demands of traceability with this method if compared to the ICP-MS. The method itself ends up with a size-separated mass concentration of elements in an aerosol. Here is a view on the cascade impactor designs. As I said, we used two different types. One is the May type cascade impactor, which has 9 stages ranging from 0.1 to 18.3 micrometers in cut points. We may use round or square silicon wafers, which are cleanable, reusable. And these wafers have very smooth surfaces, as all of you know, and they are very good for TXRF or GRXRF. And these wafers are mountable on steel insert frames, and on the other end, also acrylic or quartz discs are also possible for use in this type of cascade impactors. And of course, you may, if you wish, apply elemental standards and adhesives, elemental standards for making TXRF analysis or quantitative TXRF analysis easier, and adhesives if you take care about bouncing effects, want to prevent bouncing off particles, which may have the effect that particles are not collected at the right stage, but may end up in another stage which is not corresponding to the actual size. The CATI impactor is a commercial product which has 13 stages ranging from 30 nanometers up to 10 micrometers. And the carriers are always are of a different shape. It is acrylic discs of 30 millimeters diameter, 3 millimeters thickness. And you may use acrylic discs, as I said, or also designs where you apply round silicon wafers. It is also possible, or you may also use quartz discs, which have a surface which is smooth enough to be good for TXRF. Okay, so what is the main issues here? If you go to the May type design, that is slotted, that has slotted nozzles, and the deposit will be in form of stripes onto the carrier, and these stripes have different diameters in the different stages, as indicated here for 3 stages. On the other end, we have the Ducati, where the deposition structure is an arrangement of dots on which are shown here. The stages have different patterns, different deposition patterns, and it might be the case that, as indicated here, these patterns are not fully illuminated by the incident XRF beam. So the question is here, how good is the excitation of the deposit? and how will the whole system react? How will the signal which I detect react on the fact that I have a laterally expanded deposition here instead of the usual spot-like deposition in the center of the samples? And that is also true for the stripe-like patterns. As you can see, that also in the case of stripes, it might be so that not all the material is excited. That is something which has definitely effects on the excitation efficiency and also on the detection efficiency. And so it is a question which have to be cared with definitely, and it requires corrections. Of course, also the question of total deposited mass will influence the importance of matrix effects, which may have an influence also on the total signal strengths. Matrix effects occur if, for instance, the sample is overloaded, insofar that the interaction in the sampled material itself has an effect on the TXRF signal and then on the TXRF quantification of the elements in the sample. Well, let's see how we did the application of this TXRF in the field. We made a field campaign in September 2018, so quite a while ago. Nevertheless, we still have lots of samples to be analyzed. The field campaign took place in the city of Cassino in Italy, where we had a moderate PM10 air pollution at that time. And well, that is a small city. There is no heavy industry in that area. We did aerosol sampling by PM10 filter sampling and lab-based ICP-MS. That is the standard way. Actually used 2 PM10 samplers and had 4 qualified ICP-MS labs doing the analysis. On the other hand, we used the 2 impactors, which I've shown before, and did the first measurement with the on-site TXRF device from Buka, the PicoFox S2. We took care that we had exactly the same locations of all the devices, all the sampling devices, and all exactly the same conditions and sampling intervals. Although the main difference was then in the sample flow. So technically it was not able to operate filter sampling at the same sample flow as the cascade impactors, but that did not have a strong effect. So here's a shot on the side. So you see city of Cassino is right in the middle of Italy, and here on the balcony of that building of the local university, we had these arrangements of instruments. These are the 2 PM10 filter devices, and here are cascade impactors. These are 2 Ducati impactors, and here you see the my-type impactor. And we had a lot of other instrumentations, such as particle counters, and so just for comparison. Okay, here is a bigger shot of the impactors, and yeah, on this balcony, we let operate the instruments for quite a while, for several time slots. I will later come back to that when I compare the results. Let's just talk for a moment on calibration and traceability strategies, which we applied here. As I said, PM10 sampling and ICP-MS has quite straightforward calibration by the air volume sampling. The pumps which establish the air volume sampling are calibrated and can be controlled by independent flow meters. So that is one important issue here, and by element standards and standard operation procedures, and also interlab comparisons, you may have a qualified calibration of the ICP-MS labs. Well, on the other hand, if you use the TXRF in combination with impactor sampling, the situation is quite different. Quite usually, the application of internal standards such as yttrium on substrates, and we did a quite different way. As I said, normally these internal standards are applied directly in the middle of a substrate carrier in form of microdrops or so. And but we have a different situation here. As I said, we have a laterally distributed deposit, and therefore we tried to come a little bit closer to that situation by depositing nickel test aerosols on the samples from the Ducati impactor, and then did a reference qualification of these deposits at Bessie by XRF mapping. And then we got by this correction factors for the Picofox S2 geometry by comparison. And this enabled us to do the correction of the field results, which we got from the Picofox in the field. And then we have been able to compare these corrected results with the ICP-M results. And that I will show later. And just for information, that has been shown several times here and in other occasions, this is a device where the mapping scans have been done at the synchrotron, at the Bessie 2 synchrotron from our PDB colleagues. And well, here are some of the results. I do not show all the data we have, but here just representing the stages 2, 4, and 11 of the Ducati impactor. And for each of these patterns, we did a scan. And here you see the results when we use the test aerosol of nickel, which we deposited. We see that we are able to do a quantitative mapping, which also shows the structure of the deposit here. If you compare stage 2, where we have 4 concentric rings and dots on these concentric rings, this is also visible in these scans. And again, if we have here stage 4, which has only 2 concentric rings, again, the scan pictures show that the structure is different. And this is particularly visible if we go to stage 11, where only 3 areas of deposition are existing. And if you look with sharp eyes onto the mapping diagrams, you see these 3 areas also in the mapping data. Yeah, we can measure by this the total deposited mass of nickel, which have been slightly different in the stages, but nevertheless, there was a clear quantification by these mapping technique, and we now could compare that, or that is the total mass on the different stages of the Ducati impactor. And then we could compare that with the first uncorrected results from the S2-TXRF. And then we got empirical correction factors, which we used to re-correct the Ducati field sample and results accordingly. And in the next slide, I will show you the results. I have to say that the field sampling schedule comprised up to 9 runs of different lengths, where we collected on one hand on filters, on the other hand on the cascade impactors. And well, sometimes you may face that even with the standard methods, there are problems, such as in the field campaign in Casino. You see that the ICP-MS results showed very large uncertainties for several runs due to the fact that we had the misfortune of contaminated filters. And that was something where we have been a little bit surprised about, because we did blank checks on the filters before, but nevertheless we had to face there was a contamination problem. So these runs have not been good for comparison, and we only took the good runs where ICP-MS showed reasonably low uncertainty in the measurement of the different pollutants, of the different key pollutants which we wanted to determine here. So that is runs 6, 7, and 8, which we took out here. And here's the table of TXRF results, which we got when we used the TXRF samples for these runs. And again, I would like to point out that the sampling time was exactly the same for both the filter sampling and the cascade impactor sampling for TXRF. And now we are able to compare the ICP-MS results with the TX results, which have been corrected, as I said, and end up in such a nice plot for the 3 runs. Well, TXRF is the black squares, the ICP-MS results are the red squares. Well, that's the logarithmic Y scale, of course, but you see a nice correspondence of the elements of several elements with respect to mass concentration measured by TXRF and by ICP-MS. While that is something which we ended up with after an empirical correction, and how good is it now? You can see that for some elements it is not satisfying at all, because for instance, the separation of arsenic and lead was nearly impossible, or is not satisfying at all. So the inaccuracy of these results is clear, nothing to debate about. And also, surprisingly, vanadium was not very good, and that is partly due to the standard fitting routines which we used here, and there's some potential for improvement if you improve the routines, but that is a different story which we work on in the future. But on the other hand, there are several, or the majority of pollutants of the metals here listed, where the deviation between ICP-MS and TXRF is not so high and is in the range of 40%, which seems to be quite acceptable within the EU. And that is quite a nice, encouraging first result, which we got, which motivated us to do further research into this technique with respect to optimize the pattern structure on one hand, and also with respect to optimizing the analysis, of course, of the deposits to better understand the different effects which may occur, such as I have listed mainly the effect of the lateral distribution of in the different samples, which have, as you have seen, quite different geometries. The lateral extension goes up to diameters of 9 millimeters in the case of the Ducati impactor. And well, that definitely has strong consequences, which have to be better specified, as we did here as a first experiment. All right. So the conclusions can be summed up here. We may have definitely better deconvolution strategies for the spectra in order to better identify and quantify different elements. That is especially true for arsenic and lead. And at the end, I would say at the moment, the result is that the EU standard method and CIS TXRF is fairly well comparable, well, indicating that there's a lot to do to further improve the comparison between these two methods, because we want to fulfill or we follow a strategy to better bring these two methods in line, and to show that TXRF combination with cascade impactor sampling is more or less as good as the standard method, but offers the benefits which I have shown to you in the beginning of my presentation. So now it's time is running. I would like to show some additional results which are nice for the ambient, for the studying of ambient aerosols. That is the temporal appearance and disappearance of several elements. As I said, we can do can analyze the element distribution in the different size fractions, which is shown here. And if we now compare the runs, such as the night run over 14 hours on the 20th of September in 2018 with the day after, the morning run, and the afternoon run of the day after, you may see that the elemental fingerprint of the aerosol slightly changes. So several of the elements will increase in mass concentration in the aerosol, and that is quite nice, and it is something which is understandable from the environmental point of view, because some of the activities which are related to the emission of these elements just start again during the morning and come to rest in the night. So, for example, sulfur here, and also silicon and other elements will come up stronger in concentration during the day. And that is quite a nice result, which shows the ability of this method really to follow the chemical changes in an aerosol during time or over time. That is nice if you want to follow local emission sources, which have probably a very significant emission profile in terms of element. And you may then be able to distinguish that specific contribution from a background contribution in the aerosol pollution, which may come from other sources. Okay, I'll just go through that very quickly. And would like to show another result. I mentioned that we have different designs of cascade impactors here, and we have compared these two cascade impactors quantitatively, and here the difference is shown between these two. And despite the fact that these impactors have different number of stages and different cut points, the correspondence is within plus minus 40% among these two impactors over a large concentration range from 1 to almost 1,000. You see that the relative deviation between these two impactors can be held below 40%. That is a quite nice result, which we did not expect to be so good. I must confess that my impactor results have not been measured with it as S2-TXRF, but in the lab at MPAEK. But that should not play such a big role in the comparison here. Okay, and also the size distribution of elements are more or less the same when you use the data from both of these impactors. Well, of course, there are slight differences, and especially at the very coarse end of the particle size range, you see huge differences, which point to a slight problem here. As I said, we have a cut point of around 10 in the last stage of the Ducati impactor, around 10 micrometers. So that means that even larger particles than 10 micrometer may enter into the impactor, may then also be counted by the TXRF. And so you have to be careful that you do a correction for these effects. And we did that, or we tried to do that, but that results again in a kind of bigger discrepancy between these two impactors at the coarse end. But we have, for several elements here, quite nice correspondence, even though that the geometry of the deposits are slightly different, and then that we use different TXRF spectrometers here. So that is again nice and encouraging results that just the first shot and the first comparison of these impactors worked so well. Okay, so we think that we have proven that we can apply these techniques, that we can do all the technical steps, all the operational steps, and we think that the TXRF combination is a worthwhile tool for AQM, for air quality monitoring, but it, of course, needs some further developments and improvements, and some of these are listed here. We have to determine, for a better analysis, fundamental parameters for the TXRF spectrometers, which we may use. We definitely have to think about how to correct for a deposit mass and structure. So you may imagine that the particles which are deposited do not form layers or do not form very regular structures. The deposition pattern is regular, but in each of the dots where the particles pile up, there will be a very irregular structure, and this has consequences for the TXRF quantification. So that is something which we have to think about, and I pointed out already the importance of calibration, and we, in an ongoing project, in the ongoing AeroMed 2 project, we work a lot on reference multi-element samples for a proper calibration, which also consider the influence of the deposit structure and probably overloading, and how we can determine the case of overloading of a sample, and probably then are able to determine whether a sample is good for TXRF analysis or have to be excluded because of the situation that the material on it is too much simply. So that is a question of what is the lower limit of detection and the upper limit of detection, which is not only something which is given by the TX itself, but by the interaction of the structure of the deposit on the substrates and the TXRF abilities. And one thing which is not mentioned here is if you go from TXRF to GI-XRF, which some of the mobile TXRF instruments allow, then you learn a lot more about the structure and a lot more about the limits of the method and of the chances for a proper quantification of a given sample, and that is something which we definitely at the moment work on and did some progress so far, but I'd like to present that in a later presentation, which I probably have the chance to give. All right, let's just briefly, if the time allows, go to the other application examples, that is the analysis of laser printed particle emissions. Laser printers emit sub 300 nanometer particles during operation, and that is mainly due to the heat stress of toner and paper, which is occurring during the printing, during normal printing. And of course, these emissions pose a potential health risk, and that is why we care about it. And these particles consist almost completely of recondensated organic material. And the question arose to which mass fraction non-organic components are in the aerosol. And we try to find out element footprints of the involved materials, such as the toner and the paper, and try to find out by identifying these footprints either in the materials and the aerosol samples, which of these materials may contribute to the aerosol generation. This is not only science, but it has regulatory relevance, of course. For instance, titanium dioxide is a very popular white pigment, and it is by the EU REACH suspected to be carcinogenic, and total particle mass below 10 micrometers in size may not exceed 1% in a powder. So if there's a chance to become airborne, this limit holds for all the materials, and that is quite important for many pigment applications in a broad variety of industrial products. So that has immediate relevance. And you may imagine that if you detect titanium dioxide as a nanoparticle in an aerosol, that will stir up some questions. Okay, what did we do here? Here's on the left-hand side a laser printer, and as I mentioned, there are several spots where mechanical stress and heat stress will occur. And we put that printer into a 1 cubic meter test chamber, which has a constant air exchange of 16.7 liters per minute, or 1 air exchange of the full volume per hour. And we put that laser printers in here and plugged in some aerosol sampling devices here, cascade impactor and other devices, and also an aerosol spectrometer, which is allowed for a size distribution and number concentration measurement. And yeah, then we did some measurements, and you see that the concentration, the total concentration in the range from 0 to, let's say, 300 nanometers goes up immediately when printing starts, reaches a level, and then when the printing stops, goes down exponentially. That is a log plot here. So linear line indicates an exponential decay. And that is due to the losses which occur due to the air exchange and other losses which may occur in the chamber. Here's a typical size spectrum over time of such an aerosol emitted from a laser printer. And then we can do a straightforward analysis from the measured total particle number concentration, C of T. We may then calculate the total number of particles emitted during the printing process when we also plug in the particle losses. And for the impaction process, we can calculate the number of sampled particles just if we know the impactor sampling rate and if we know the concentration over time. That is NK. And if we now then combine these information together with the detected element mass in a TXRF sample, we may end up with the mass of an emitted element. And that was our goal. And I will show you some results here. These are a comparison of masses in ppm or mass concentrations in ppm for toner on the left side. So toner is the powder which makes or in other words, the ink of a laser printer. And we compared this toner signature or fingerprint with the fingerprint of the PM 0.7 fraction of the aerosol. And there we see some similarities, but in different quantities. And we can identify some very typical elements here, such as silicon. Silicon is very representative for talcum and for lubricants and separation agents, which makes paper sheets easier separatable from each other. So that is quite important ingredient here. We may identify other things as titanium, as I mentioned, that is white pigment. Unfortunately, both in the paper and in the toner, we identified, for instance, bromine as a flame retardant. That came as a surprise because bromine is not allowed in a toner. It may come from the structure of the printer itself, which may become properly heated to an extent that it emitted bromine. And if the structure consists of polymers, for instance, then bromine is a very typical flame retardant. Not allowed any longer, but anyway, it was there in the aerosol. And magnesium is also a very typical ingredient for paper bleaching, for instance. So we have here, if we compare these two things, more or less the same appearance of typical elements, but in different proportions. And this direct comparison shows, for instance, that that we have a higher concentration of magnesium in the aerosol if you compare it to the toner. So that means there is another source for magnesium, not only the toner, but most obviously also the paper, which is contributing to the high content of magnesium in the aerosol. If you go to the elements which appear in very small concentrations, we see, for instance, cerium here in the toner. Cerium is well, quite expensive material, but it is in the toner for purpose. It is there as an additive which eases the separation of the toner from the photo drum in the printer, so it makes it easier to separate the particles from this drum and to regain the excess particles back into the particle container. Well, that's very typical for toner, and we see also this here in the aerosol. So that is an indication, among others, that the toner definitely contributes also to the aerosol. Okay, and what was important here is that we have been able to compare that to typical uptakes in a city, and compare these uptakes of different elements in the city environment with uptakes which can be expected from moderate laser printing activity. And we could do a first estimation of the non-evaporable substances in laser printer aerosols, which have been determined in the order to be in the order of less than 2% of total aerosol mass. And if we now combine this information, we end in a comparison of the daily uptake from outdoor air in a city environment and the daily uptake from moderate laser printing activity, in order to answer the question, well, is that so dangerous? Does laser printing activity really pose severe additional environmental health risks? And the answer is most likely not, because as you see, there is only very, very moderate increase of the moderately higher uptake from laser print activities to that dose of particles of elements which you already get in an environmental in a city environment. And that was quite important to learn, because the laser print emissions have been in the past decade under high debate, and then there have been people claiming severe health effects from these exposures to laser printer activities and aerosols, and others who argued against it. And well, the only thing to answer that properly is just analysis like this, that is the comparison of the aerosol compositions as we did here. And TXRF is quite a nice tool for this, because it allows for determination of all these elements in quite weak samples. So the total amount of sampled material in these samples are very small. So at the lower end of detection, at the lower limit of detection for ICP-MS. So in this case, TXRF was the method of choice. All right, what is the conclusion here? We could say that the total inorganic mass, or the non-evaporable substances in a typical laser printer aerosol, is in the order of less than 2%. I forgot to mention that it is higher in the toner, so it is a depletion of the non-evaporable substances when during the printing process. So not all of the non-evaporable substances in a toner will become airborne. That is a message here. We have shown by the comparison that the concentrations are not posing a high or critical health risks, and we could do a kind of source assignment by several elements which either point to toners or papers as sources of the aerosol which is coming out of the laser printers. So we can say that the thermal and mechanical stress of the paper is definitely contributing to the aerosols. That was a question which was very much controversially debated in the community for a while, because many people just stated, oh, it's only the toner. And other people said, oh, it's just only paper dust. And well, it's both, that's for sure. And well, when we combine now TXRF with other indoor chemical aerosol analysis methods, we see that when we do, for instance, cascade impactor sampling and have on one hand the instrumentation of thermal desorption, GCMS for organic aerosol components, that nicely adds up to the feature of TXRF for the identification of elements. And with both methods, we have a nice tool for very full scope chemical indoor aerosol analysis. Okay, that's all I wanted to show to you, and I thank you very much for your attention.
Thank you so much, Stefan. Thank you for sharing this very interesting subject with us. I think we're ready for the discussion. Who wants to start? There's Stefan.
Hi, Stefan. Thank you for the nice presentation and for really quite interesting information regarding dust measurements. I got one question regarding your comparison of ICP-MS and TXRF. I know in a lot of cases regarding ICP-MS, you measure recovery rates to test your equipments. It's a standard way. My question is in the direction, did you also try to measure recovery rates for especially for the elements where are some problems like vanadium or chromium in your measurement cycles?
Yeah, I mean, what we did is we did repeated measurements of the same samples, and then the recovery rate of that is quite nice. When we do with artificial samples, so with pipetted samples on a substrate, do repeated measurements by repeatedly pipetting the same amount of material on it, the repeatancy is quite better. So, I mean, in other words, saying that TXRF is a method which has high repeatability, and the recovery rate is at least as good as for ICP-MS if you do the things in the right way. So I hope that is answering the questions.
I think so. So in my point of view, most critical issue is the sample preparation and not so the measurement procedure.
Yeah, it depends. As I said, TXRF provides samples which are unusual for, cascade impactor sampling provides samples which are unusual for TXRF. And you have to face the challenge of laterally extended samples or deposits. And we have found out, which I could not show here because that were very recent results, that, for instance, proper positioning of such a sample in a TXRF spectrometer is of extreme importance. And that was something which we worked on it for more than half a year with our spectrometer to make sure that we are properly centered with our sample in the geometry. And if we do not do that, we have severe, strong effects on the quantification. But if we do that very carefully, the effects can be reduced to less than 8%. And that is, in my opinion, a quite nice result at the moment. Perhaps we are even more better in the future, but 8% is something which I can live with.
Okay, thanks a lot.
Thank you.
That is interesting. So I might ask right to this subject. The centering of the sample, that is the centering in the TXRF spectrometer, or is it positioning in the impactor?
Actually, it's both. I mean, you can be pretty sure that the deposit is centered correctly on the substrate, on the carrier, just by mounting the carrier properly on the holder. That is something which you can achieve just by pure mechanics. So the centering of the pattern is something which can be fulfilled or can be easily done. And then secondly, the more important point is the centering in the spectrometer. Because as I said, it does not matter for a point like centrically pipetted drop on a carrier, whether it is by let's say a quarter of a millimeter less centric. It does not count so much, but for an extended deposit, it is crucial to just do it in the symmetric way, in order, because we have to face that the excitation area and the area of laterally extended deposit is more or less the same. So we have the case where some parts of the deposit is not excited, and secondly, that the outer parts of the deposit which are excited will probably emit photons which are not detected in the detector. So that is critical, and but for that reason, that is something which we have to be very careful about. Well, that is a technical challenge or methodological challenge, and as I said, if you do the things right, you may end up with less than 8%.
Mm-hmm. Yeah, I see. Thank you. There's a question from Abdallah. Did you estimate, so there are two questions actually. Did you estimate the health risk assessment factors from the laser printer aerosols?
Well, we have been part of a study where we did exposure experiments. So BAM itself does not do health study. It's not our business, but we provide, for instance, methodology for an exposure scenario where other people which are more knowledge in doing health studies can study the health effects. So, and that is exactly what we did. We did an exposure studies with volunteers, with human volunteers, with laser printer aerosols, and found out that the acute effects on health, especially the respiratory tract effects, are not significant. That was the result of that study. If you're interested, I can give you the quotations to the papers and you can read by yourself. And I read the second question. Yes, question 2. As I showed, we may have a fingerprint of the toner. So we solved the toner in an acid and pipetted it on the substrate holders, and then we were able to identify the toner composition, and we compared that to the composition or to the elemental fingerprint of the aerosol, and then found some similarities, such as, for instance, cerium, which is both in the toner and in the aerosol. That is a direct, very strong hint to the fact that part of the toner will become airborne and will be part of the aerosol, as it is also true for the paper. So we could decide by these comparisons, and we did many more than those which I've shown to you, that it is most likely that also or both toner and paper will contribute to the aerosol. And well, if you think of recycling paper, for instance, that is a completely different issue, because we only used clean, pristine paper here for our investigations. But if you use, for instance, recycling paper, you may even see a broader variety of contributions from the paper also to different elements which have been piled up or which have been up concentrated in recycling paper. But that is something which we did not do because of the many different types of paper. Yeah, but in principle, yes, the answer to the question is yes, we did.
I have a question.
Sure, Yoon, please go ahead.
I'm very interested in titanium dioxide. So some of my colleagues in my university says titanium dioxide has some potential to be the one the second asbestos. So it may be very toxic in a sense if it is as small as nanoparticle. So, but the problem is titanium dioxide is it's too broad. It is existing any place as a paint or something. And so my question is it much suitable to observe scanning electron microscope or something to observe its shape, and maybe the particle may be 100% titanium oxide, and it is not so dilute. And so for the study of titanium dioxide nanoparticle, so the TXRF is not suitable. It's my question.
The TXRF is a quantitative method. So it answers the question if there's titanium dioxide in the aerosol and to what quantity it is in the aerosol. And the answer is it is in the aerosol and it has a given quantity. And but well, you're not done with answering this question. You have to go deeper into as you proposed microscopy to answer the question if there's pure titanium dioxide particles in their aerosol, or if the titanium comes with an organic particle as a contaminant of an organic particle. So that is something which we have to distinguish. The EU regulation follows the scenario that titanium dioxide as a pure particle will become airborne. And then there's a suspected cancer risk combined with that scenario. And that is the reason why the EU decided to classify these materials as potential carcinogenic. Not as carcinogenic, but as potentially carcinogenic. And but here, for the special case of laser printers, it is more likely that the particles are acting like a contaminant of bigger particles, rather than being pure titanium particles. It is also with the other elements. It is much unlikely to imagine, or much unlikely to happen, that all these particles are separate particles of only consisting of silicon or titanium or cerium or so, but it is more likely that these particles are in a polymer matrix, formed as a particle and released as a particle in a polymer matrix. And so the main constituent of the particles will be a polymer matrix of the evaporated polymeric toner material. That is the scenario which I think to be the most thinkable and most likely.
Thank you.
Thank you.
I have one it's a story. That means many Japanese cosmetic company try to use nanoparticle titanium oxide, and so some people who use the her skin or something to as a cosmetics, and then it is irradiated by the sunbeam. Then some problem of the skin, and the cosmetic company don't say anything, and they stop to sell. So there are so many companies, something like that, I heard. So it's the titanium dioxide has reacted with organic material to decompose by the it's as a catalyst, yeah, using the sunbeam. So it's a very big problem.
Definitely, that's something aside from aerosols, but I mean, titanium dioxide is in many cases something which should be looked at with great care with respect to health effects, such as in paints or in cosmetics or whatever else. So, but as you said, it is very important to recognize that titanium dioxide is extremely popular chemical in many products, from toothbrush to paper and everything in between. So if there is a real ban on titanium dioxide in the EU on nanoform titanium dioxide, that would be clearly a huge problem for the industry. But at the moment, it's not yet has not yet come to that. So at the moment, in titanium dioxide, when with the risk of becoming airborne, is just suspected carcinogenic. That is the acute status of the discussion.
Yeah, thank you.
Thank you.
Are there more questions? So maybe I have a question. So the EU target of plus minus 40%, that to me it sounded quite high. Is that because of these field studies? Is just so many uncertainties?
Yeah, it is high, but given the fact that you may even have pre-contaminated filters, for instance, and also have AAS as one of the alternatives to ICP-MS, well, that is obviously something which have been derived from experience rather than from theoretical considerations. And I learned that simply from the regulations that 40% is acceptable. I, as a physicist, would say, oh, well, I would like to be better than that, of course. But for the moment, it was in the focus whether we are as good as the other methods or even better. And our claim is to be better, of course, but we will see how far we get.
Okay, thank you. And maybe I have a very last one. And
go ahead.
So these time resolved measurements, they're quite attractive, I think, with TXRF, because there are only short sampling times needed. But then there's this manually mounting and so on. So have you thought about an automatic system to sample and maybe measure? Or is that something you have not thought about yet? Or
well, we do not work on it at the moment, but I definitely do think that this is technically possible.
Mm-hmm.
But it's, in my opinion, it is step 2, and step 1 is to show that the method works sufficiently with sufficient accuracy. And we are at the moment right in step 1. And if that is done with a good result, we may then think of developing fully automated systems. But I think the designs of cascade impactors, which I've seen, have this potential.
Mm-hmm. Mm-hmm.
And you know that part of the spectrometers which are out there, the semi-mobile spectrometers, have 90 have a storage of 90 samples and are fully automated. So you may mount 90 samples and do an overnight scan of all these 90 samples, and then so that is quite comfortable conditions for mass analysis, even with these devices. And yeah, you may end up in a solution to also automatically do the mounting, dismounting. That is something which I think can be solved.
Mm-hmm. Yeah, yeah.
Sorry, Ursula, there is one question from Cristrelli in the chat. She wants to ask about the bounce of effect. How you handle that?
Ah, okay, yes.
Okay,
yes.
bouncing effect, yeah. Mm-hmm. That is something which you may handle with applying additives or adhesives onto the surface of these stages. We did not do so at the moment because bouncing means that you have an inaccuracy in in the sizing, in the proper sizing of the particles. So particles end in the wrong stage. That is the effect of bouncing. So bigger particles may end in a stage where smaller particles are sampled. So the effect will be that then the size information is quantitatively probably not as precise as wanted. But for the total element concentration, this does not matter so much, because if you add up the results from all these separate stages, that should be more or less the same. And that was the first goal here, because for the comparison with ICP-MS is just simply done by adding all the stages which are representatives for the PM10 fraction and then compare it to the filter analysis. And for this type of analysis, the bouncing has not a strong effect, because it does not count whether I count a bigger particle in stage 1 or 2, as long as it is caught in one of the stages. But later on, we probably may think of better preventing bounce-off effects, and normally this is done by applying adhesives or greases or something like that. But for the moment, we have been not doing that because we wanted to simply avoid an additional risk of contamination and an additional risk of cross-talking between the adhesive and the analytes. So we have to, that is something which we have to solve later. But for the first step, we're happy to add all the stages all together.
Yep. Thank you.
Okay, let's thank you for listening. Bye-bye.
Bye.